right, so in our discussion of the kinetic molecular theory, we know that we've talked about two things that we have to assume when a gas is an ideal gas, that it doesn't take up any space and they're not attracted to each other. So then the question comes up, when does a gas not behave like an ideal gas? Okay, and let's go back to the kinetic molecular theory. It's based on those two things, that gases don't take up any space and they're not attracted to each other. So when does a gas not, so here when it talks about deviation from ideal behavior, that means when does it not behave like an ideal gas? Well, again, we assume that gases don't take up any space. So if there's a lot of gas in there, the more gas you put in there, the more space it does actually take up. And that assumption that the gases don't take up any space starts to fail. So when the pressure is high, a gas tends to not behave like an ideal gas. Because, again, there's so many particles in there, that's what's making the pressure high. There's so many particles of the gas in there that it makes the space that the gas doesn't take up, that we pretend like it doesn't take up, it actually is taking up more and more of that space. Okay, so when we say that, that the size is negligible compared to the average distance between them, begins to fail when the pressure's high, because there are a large number of particles in there that are actually taking up some of that space. Okay, so when you're at a high pressure, the gas particle size becomes more significant compared to the total volume. Okay, and so therefore the actual total volume under these conditions is artificially large, since the gas particles are now occupying a significant amount of that volume. Okay, so when the pressure is high, a gas does not behave like an ideal gas. Number two, when the temperature is low, gases do not behave as much like it as an ideal gas. Let's think about the water cycle. When water evaporates and it goes up into the sky, the water eventually begins to condense, which means it turns back into a liquid. Why does that happen? Because as you go up, the temperature goes down. And as the temperature goes down, as the molecules hit each other, they're more likely to stick together. They're more likely to be attracted to each other because they don't have as much energy. Okay, so when you lower the temperature, when molecules hit each other, they're more likely to stay together than to just bounce off of each other and keep going. So at high pressure, because the gas particles are actually taking up more of that empty space that isn't really empty, and at low temperatures, gases do not behave like an ideal gas, like ideal gases. Okay, because again, at low temperatures, the gases have less energy, and as they have less energy, the particles are more attracted to each other. Okay, and so therefore they're going to be, when they hit each other, they're going to stay together better than if they had just bounced off of each other at a higher temperature. Okay, and what that does is it makes the pressure lower than what you would expect, because as the particles hit each other, instead of bouncing off of each other and then hitting the walls of the container, they hit each other and stay together. And then once they stay together, now you've got one particle hitting the walls of the container instead of two. Okay, so whenever the pressure is high and the temperature is low, gases tend to behave less like ideal gases. So therefore, let's do the opposite. When does a gas behave most like an ideal gas? Well, obviously the opposite, when the pressure is low and when the temperature is high. Okay, because at low pressure, they are taking, we say that they don't take up any space, they really aren't taking up very much space. The pressure's so low, there's not very much gas in there. And when the temperature's high, they've got so much energy that they just bounce off of each other and keep on going. Okay, so at high pressure and low temperature, a gas does not behave like an ideal gas. Okay, and the opposite is also true. At a low pressure and a high temperature, they do behave more like ideal gases. Real easy multiple choice questions there that they could throw at you about which of the following gases would behave most like an ideal gas, or which gas under the following conditions would behave least like an ideal gas. Okay? Now, one of the things that affects this as well is about the attraction between molecules, okay? Is what if you have different gases at the same temperature and at the same pressure? Which one would you expect to behave more or less like an ideal gas? Is going to come back to, we kind of introduced this a while ago, and we're going to get to it in a lot of detail here in just a few more videos. Okay, but one of it has to do with intermolecular forces. Okay, those are the forces of attraction between one molecule and another. Okay, if one gas has stronger intermolecular forces than another gas, and they're at the same temperature and the same pressure, the one with the stronger intermolecular forces will deviate, which means act less like an ideal gas. Okay, why will it do that? Because stronger intermolecular forces means they're more attracted to each other. So when the pressure and the temperature are the same and one molecule has stronger intermolecular forces than the other, that one will act less like an ideal gas or will deviate more from ideal behavior. Okay, so we don't know why yet, but you're going to learn that SO2 does have stronger intermolecular forces than O2 does. So that means that a molecule of SO2, something like this, is going to be quite attracted to another molecule of SO2. And there's an attraction between this molecule and this molecule. And that attraction is stronger than the attraction between, here's one oxygen molecule and here's another oxygen molecule, between the attraction between those two. So it means that this molecule is more attracted to that molecule than O2 is to itself. So if they're more attracted to each other, again, we assume that there are no attractions between them, right? That's part of the kinetic molecular theory. So therefore, SO2 will deviate more from ideal behavior or from being an ideal gas because SO2 has stronger intermolecular forces. Okay, there's a stronger attraction between SO2 and other SO2 molecules than there is between O2 and other O2 molecules. Okay, let's keep going here. Speed, the speed of molecules. Okay, and also these, the law of effusion and diffusion, all are based on two things. Okay, here's the equation. You don't need to know it. Okay, it's not given on the equation sheet, and you're not going to be asked to calculate the speed. They do sometimes refer to it as the RMS speed, the root mean square speed. There's the root right there, the square root, and mean, it means the average. So again, the equation does not matter. The two things you have to know are there's two things that determine the speed of a molecule. Number one, you can see it right here, temperature. Okay, the Kelvin temperature, and notice it's on the top of the fraction. Obviously, the higher the temperature, the faster the molecules are going to move, the faster the particles are going to move. Okay, so one of the things that affects the speed of a molecule is the Kelvin temperature. And the second one is on the bottom here, and that M is the molar mass. And again, notice that's on the bottom of the equation, which means the greater the molar mass, the smaller the root mean square speed. Okay, the slower that molecule moves. So molecules move slower when they weigh more, when they have a larger mass. Okay, and that makes sense. Think about somebody like me who's a big guy versus somebody who's really, really skinny and small. I move slower than smaller people do. Okay, and that's how it is with gases too. The bigger they are, the more massive they are, the slower they move. So, temperature and molar mass, that's what you need to know. Okay, now what that does is it affects both of these, effusion and diffusion. So effusion is, let's say you have a balloon and you put a piece of tape on it and you poke a tiny little hole in it. Or we'll talk about a car tire that's filled with different gases, oxygen and nitrogen and things like that. Okay, those things, that balloon and the car tires, over time will slowly start to lose, the gases will start to escape. Okay, and so that's what it is. Even when you have a very small opening, like a little pinhole in a balloon or even in a tire, you know, there are little holes in it that gases do escape little by little. You do have to keep adding air to your tires over time. Okay, that's what effusion is. Effusion is gases escaping out of a little tiny hole. And what's the rate of effusion determined by? This right here, the speed. Okay, the faster a particle is moving, the more likely it is to hit that hole and escape and go out of the balloon or car tire or whatever. Okay, so two gases at the same temperature, whichever one has the smaller molar mass, is going to effuse faster. So what effuses faster, H2 or HE? Well, H2 has a molar mass of 2, again, assuming you're at, let's say, 25 degrees Celsius for both. So hydrogen has a molar mass of 2, helium has a molar mass of 4. Which one's going to effuse faster? Hydrogen. Why? And how would you explain it? The smaller molar mass of hydrogen allows the molecule to move faster and therefore will effuse at a greater rate. Okay, that's a great way to answer that question. Okay, diffusion, very similar, but diffusion is like you put on some cologne and the people close by you smell it, and then it slowly spreads out, or put some perfume, and everybody will eventually start to smell it. But as it spreads out, it becomes less and less concentrated. So diffusion is just a gas that is just spreading out over time. And which one's going to diffuse the fastest? Same exact thing. It's based on the speed. Okay, it's based on the temperature, and it's based on the molar mass. So whichever one again is as the smaller molar mass, which one's going to effuse faster, O2 or CO2? Well, O2 has, again, assuming they're both at the same temperature. So O2 has a molar mass of 32, CO2 is 44. Which one's going to diffuse and effuse faster? Absolutely O2. And again, why? The smaller molar mass of O2 gives it a greater speed, and therefore it effuses and diffuses faster than CO2 would. Okay? And that's basically what we just talked about here. The smaller the molar mass, the faster they effuse and diffuse because they are moving faster. Okay? Helium escapes faster than oxygen does because helium has a smaller molar mass. Therefore, it moves faster, it travels, it's got a greater RMS speed, you could say. Okay? And helium would diffuse faster than oxygen for the exact same reason. Okay, and then the last thing that we're going to talk about here is just talking about how a gas works in terms of solubility. Okay, if you think about, if you take a bottle, a 2 liter of Coke or something like that, and you heat it up and you open it, it's going to be way more fizzier than if you have it really, really cold. Okay, and that's because gas solubility decreases with an increase in temperature, which means that when you lower the temperature, the gas tends to be better dissolved in the liquid. The higher the temperature, the less it dissolves in the liquid. Okay, think about it in terms of energy. If you just if you drop a 2 liter on the ground and it moves all around, you've increased the energy inside of there. You may haven't increased the temperature, but temperature is another form of energy. But you've increased the kinetic energy inside that bottle by moving all those particles around. And if you open it, you know what happens. It comes squirting out the top because, again, you've increased the energy. You've increased the amount of gas that's going to escape from that bottle. If you like your pop really, really carbonated, is how we would say it, then certainly you're going to keep it really cold and you're not going to move it around much when you open it. Even when you pour it, you're going to pour it really slowly. When you pour it really slowly, it doesn't, again, you're trying to keep that energy nice and low and keep those gases in there because, again, when the temperature's low, gases dissolve really, really well in liquids, but as you increase the temperature, they become less and less soluble.